Hi, I wanted to do one last quick short video talking about one last important concept that relates some of the things we've previously talked about. In particular, I want to talk about the Jacobian that we talked about back in chapter 8 and how it relates to matrices. In fact, it is really the thing that we've been talking about as the Jacobian is better thought of as the determinant of a Jacobian matrix. So first, what am I talking about? Let's remind ourselves what the Jacobian was. So that was when, if we wanted to talk about, say, the volume of some integration element in, let's say, right now, the IJK basis. So there's another connection to what we've been talking about. We would, of course, just think about some little kind of cube of size dx on a side, dy on a side, dz on a side. And this would be, we would have some limits in each of these directions, x, y, and z, and that would be it. That would be our volume. Of course, if we were in a different basis, though, say we were in the rho hat, uh, phi hat, z hat basis of um, cylindrical coordinates, we could set this up again. It would still be a triple integral, and we would still have a d rho, a d phi, and a dz. But now we actually need to put something in here, and this thing that we put in here, which in this specific case was a rho, um, was called the Jacobian. And I want to show where that comes from and why, and how we could even perhaps derive whatever it should be for any given set of coordinate transformations. Because these things are really going to add up to the same thing if we're talking about the same total volume being considered. And it's just about what set of coordinates are we using to integrate this thing, whatever it is, this volume. So we worked this out geometrically to figure out what this had to be, and this came from the fact that, well, this d rho has units of length and dz had units of length, but d phi was just an angle, and so in order to get a length out of it to create this volume, we needed to multiply by rho, and we had worked this out geometrically in class. But say, and we could have figured out at least in terms of the dimensionality that it needed to have a distance in there. But why was it exactly rho and maybe not 1/2 rho or something like that, or pi times rho, something weird. We can figure this out though by considering how these coordinate systems are related to one another. So we know x equals rho cosine phi and y equals rho sine phi. Of course, this comes from considering the position here, x and y. X and y also must be equal to rho cosine phi, rho sine phi. When we break it up into these two coordinates, maybe I'll use a different color here. This length there, which is the x coordinate, is the adjacent side to this angle phi, and this distance, which we know is rho, is the radius in cylindrical coordinates. And of course, this side here, which we know is the y coordinate, is the opposite side of this right triangle that we produced. So that's how we know these in the first place. But what we can do now is write the Jacobian matrix, often designated by J, is a series where the elements of this matrix are each one of the partial derivatives relating these quantities to rho and phi. So if I fill this out as dx d rho and dx d phi, and then the second row would go dy d rho and dy d phi, like that, then this Jacobian matrix, if we find the determinant of that matrix, we can say the determinant of J would be dx d rho times dy d phi minus dx d phi dy d rho, like that. And of course, we know these functions, so we can actually evaluate these derivatives. And maybe I'll even take a step back and evaluate them um, within this matrix. So dx d rho is just going to give us cosine phi. Dx d phi, so we would get here rho, and go from phi here. We go cosine, cosine, we'll go to minus sine, like that. Dy d rho is again sine phi, and then dy d phi, we have now sine going to cosine, like this. So when we evaluate this, we have cosine phi times rho cosine phi minus, now this tells us dx d phi, which is this one, minus rho sine phi times another factor of sine phi. Then we get rho, and I'll factor that rho out because there's a rho in this term as well. We get cosine squared phi plus sine squared phi, which is just rho. So that determinant of this matrix is just rho, the cylindrical radius. Now remember when we talked about um, determinants of matrices in class, we talked about how they related to the amount of area of the shape. And so now if I think about it in terms of just x and y, there's some little box x with side, sorry, dx, and some little side dy, like that. But if I need to convert this amount of area into spherical, or sorry, cylindrical coordinates, or maybe just polar coordinates is really what we've been working with here, I would get an element that looks like this. Some here, d rho, and this side length is going to be basically, sorry, rho d phi. And that is where this comes into play. The scaling depends on how this area contained here depends on how far out in radius you are. Because if I keep this d phi the same and kind of draw out these lines at different radii, and I keep some area over here is going to be much bigger than the same corresponding area in here. And what I should have done here is keep my d phi, or my d rho, the same. So d rho here is about the same as the d rho I had here, but now we have more total area because we're going out further in radius. And so this is where that comes into play, that Jacobian determinant valued at rho means that the area that I'm creating here in this infinitesimal d phi d rho thing actually scales up as we go out in terms of the rho, the radius in this polar coordinate. So this is where this really comes from. And if we had done the exact same thing, but talk about spherical coordinates, we could have ended up with deriving the fact that it ends up being r squared. The Jacobian matrix determinant for spherical coordinates is r squared sine theta, theta being the polar angle. And that shows up when we do these integrals. So now if this is spherical coordinates, my volume integral there would be r squared sine theta d phi dr, like that. And so that's where this Jacobian comes from. You can define it in terms of this Jacobian matrix made up of partial derivatives relating two different coordinate systems. And so that's something that you can look up the Jacobian for any given transformation. What I want to then do here is maybe real quick also share a little bit of how this relates to my own research. This is a code paper. This is where the actual um, I do simulations, and the code that the simulations run solves this set of differential equations, which is the ideal magnetohydrodynamic equations. And some of these things that you'll see here will look a little bit familiar. You got some partial derivatives. You have here now a divergence of a vector field. This is actually the momentum of that field, or momentum density of that field. This is just the equation of continuity that we actually talked about in class. We've got some cross products here. We've got gradient of a scalar field, things like that. But the details aren't super important. What is important is we can write out these equations in terms of a conservation equation, meaning these things are conserved, and then these are the fluxes of those things moving in and out of any volume of physical space. So now we've got two vectors here, but what we can really define is a Jacobian matrix A, which is a function of all those conserved quantities, and we then try to figure out what are the eigenvalues and eigenvectors associated with that Jacobian matrix. And they actually have some real important physical meanings here, that the actual eigenvalues listed here, there are 7 of them for this equation. And those 7 eigenvalues correspond to different wave velocities for each one of the possible characteristic waves that move through a magnetized medium. So not only do you, in that context, you get sound waves, but you also get waves of the magnetic fields and waves going along or perpendicular to those magnetic field lines, which move at different velocities. And of course, then there's even things like, what are the eigenvectors associated with those eigenvalues? And we find those, and they're important for actually solving this set of differential equations so that we can then evolve the simulation forward. And so here are a bunch of eigenvectors showing up and eigenvalues in a real science context that I use in doing my research on studying radio galaxies and extragalactic astrophysical scenarios, particularly related to galaxy clusters. So that was just a quick aside showing some stuff about how these matrices can be used in other contexts. So hope that was useful.